An acid neutralizes a base to form a salt and water. Neutralization occurs at the equivalence point when the amount of acid added to the base is chemically equivalent to the amount of base. The endpoint of a titration is the point at which the indicator changes color. To find the equivalence point, we choose an indicator which changes color at the same pH as the endpoint. 3 indicators are available to us in a school laboratory: methyl orange, bromothymol blue, and phenolphthalein. Their colors and pH at the endpoint are shown in the table. The endpoint of methyl orange is at pH equals 3,7. For bromothymol blue, it is at pH equals 7. And for phenolphthalein, it occurs at pH equals 9. The neutralization reaction is complete at the equivalence point. There are chemically equivalent amounts of acid and base present at this stage. The products of neutralization are the salt and, of course, water, and sometimes a gas such as carbon dioxide is released. It is those types of salts formed when the pH at the equivalence point is not equal to 7 that hydrolyze in water. Hydrolysis of a salt is a reaction between an ion of the salt and water, in which water is split into its ions. This generally involves a change in pH of the solution. Soluble salts are strong electrolytes. They dissociate completely in water. Salts formed from the reaction of strong acids with strong bases dissociate without affecting the pH of pure water. The equivalence point of a titration of strong base with strong acid is pH equal to 7. These salts are neutral salts. They do not react or hydrolyze with water when they dissolve. Soluble salts of strong acids and weak bases also dissociate completely in water, and they form acidic solutions. When ammonium chloride dissolves in water, bromothymol blue indicators turn yellow. Ammonium chloride is the salt of a strong acid, hydrochloric acid, and a weak base, ammonium hydroxide. The equation shows this reaction. The reaction of a strong acid and a weak base forms an acidic salt and water. When ammonium chloride dissolves in water, it breaks into its ions, the ammonium ion NH4+, and the chloride ion Cl-. It is the ion from the weaker substance which reacts with water. In this case, it is the ammonium ion that reacts with water because ammonium hydroxide is a weak base. The ammonium ion is the conjugate acid of the weak base ammonia. The ammonium ion releases a proton when it reacts with a water molecule. It forms a hydronium ion. The increased concentration of hydronium ions causes the pH of the salt solution to be acidic. How is this possible? The ammonium ion acts as a stronger acid than water in the hydrolysis reaction. It releases its proton, therefore it acts as a Bronsted-Lowry acid. Water molecules receive and bind protons to themselves. Therefore, they react as Bronsted-Lowry bases. An equilibrium is set up in the solution. Both reactions occur at the same rate, but the equilibrium lies to the right. There is an increase in the concentration of hydronium ions when ammonium chloride dissolves in water. Salts formed from the reaction of a strong base and a weak acid also undergo hydrolysis. These are salts such as sodium ethanoate, potassium oxalate, and sodium carbonate. These soluble salts of weak acids and strong bases dissociate completely in water. The anion, which is in the conjugate base of the weak acid, reacts with water, raising the pH of the solution. Let's take sodium carbonate as an example of hydrolysis. In water, sodium carbonate dissociates into its ions, sodium and carbonate. The sodium ion does not react with water. It remains in solution as a spectator. It is the carbonate ion which originated from a weak acid that reacts with water. The carbonate ion is a relatively strong Bronsted-Lowry base. It is able to attract and bind with a proton, and it does this by pulling an H+ ion of water molecules away from the hydroxide ion. The concentration of hydroxide ions in solution increases. The ionic product of water ensures that the product of the concentrations of both hydronium and hydroxide ions remain equal to 1 × 10⁻⁻14. Therefore, the hydronium ion concentration decreases. And we know that a low concentration of hydronium ions means that the pH of the solution increases. Salts of weak acids and strong bases hydrolyze in water to form slightly basic solutions. Let's now consider the hydrolysis of potassium ethanoate. Potassium ethanoate may also be called potassium acetate. Its IUPAC name is actually potassium ethanoate, but some textbooks, teachers, and chemists still call it by its older name, potassium acetate. Can you work out how potassium ethanoate hydrolyzes in water? In what range will the pH be? Pause the program to give yourself time to work this out. Potassium ethanoate splits into its ions when it dissolves in water. The ethanoate ion reacts as a relatively strong base with water. It strips the proton from the water molecule, leaving the hydroxide ion in solution. The increased concentration of hydroxide ions causes the concentration of hydronium ions in solution to decrease. This makes the pH of the salt solution slightly basic. To sum up hydrolysis of salts, remember that not all salts hydrolyze in water. The salts of strong acids and strong bases form neutral solutions with pH equal to 7. Salts of a weak base and a strong acid form slightly acidic solution. For example, ammonium chloride solutions are slightly acidic. Ammonium nitrate solution will also have pH less than 7. Salts of strong bases and weak acids form slightly basic solutions. For example, sodium ethanoate, potassium oxalate, and potassium carbonate will form slightly basic solutions. You may be required to predict the pH of salt solutions and to explain your reasoning in words and by writing appropriate equations. Take time to practice